Please be seated.
Today I would like to talk a little bit about what my research is all about. But I want to first start out to tell you about the No Shave November. And most of us take shaving for granted. We don't even think about it. If you go to the store, you can buy shavers that have 5 blades or, super sophisticated electric shavers. But if you look into the history, at some point, shaving was a professional job. You would have a barber that knew how to sharpen the knives and would know how to shave people. And actually shaving was really dangerous. If you would cut yourself, you could die because we didn't have antibiotics yet. So something that used to be something very special and where people maybe could afford to get shaved once a month, now we don't even think about. And so in my words, shaving has been democratized. So what does democratization mean? Well, democratization is the process of a good or a service to get a wider audience over time. So if you see in this picture, first it starts out with a red line where this is not very accessible. Only the elite, only the 1% has access to the goods. And then as time goes by, the product gets cheaper and more people can access it. One consequence of this, one consequence of growing like this, is that the quality generally goes down. So at some point, the quality of the good will be good enough. And I'll say a little bit more about that later. So let's look at an example of democratization, and that's education. So if you look in the Middle Ages, there were professors wearing black robes, teaching students one-on-one. Probably the students were, the children of kings and noblemen and rich people. Then in the 20th century, in the 60s, the students fought hard to make education accessible, but it is still kind of elitist. Like in the Netherlands, you still have to go to VWO or something, so it's not everybody can get an academic education. But the internet is changing that. The internet is changing this fast, and now with things like the Khan Academy or the MIT Open Courseware project, everybody can get access to education. And even in the third world, when kids have the 1 laptop per child, they can access education. So I think education is now really available to everybody. Let's look at another example, food. When we were still running around in the savannas, it was really hard to get food. You had to work really hard for it. But today, you can walk into any supermarket and there's an abundance of food. As you see also is that calories have become cheap, but at the expense of nutrition. And that's why there's so much obesity, because you can get for $1, you can get a lot of calories, but it's not very healthy. Another way to view a supermarket is not as something where you go to buy stuff, but as a pantry that you rent out and that somebody else takes care of. So you just go to your pantry and it has an infinite supply. You don't have to think about it. If you need 1 gallon of milk, you get 1 gallon of milk. If the next day you want 2 gallons of milk, you get 2 gallons of milk. So it's an elastic, infinitely scalable pantry that you rent and that you share with many people. That's a very different way of looking at a supermarket. You just see it as an extension of your kitchen. So I would argue that everything in the Western world, at least, is democratized. You open the tap, you get clean water, you can get good health care, electricity everywhere, clothing is very cheap, transportation, housing. So everything has been democratized that we care about. So then, what is this whole cloud thing? Well, that is the democratization of computing. So computing started out maybe a long time ago with the Chinese, where they had like abacus, and there were a few people that knew, the Chinese remainder theorem that could compute. Then in the 1950s, we had big mainframes. In the 90s, we had personal computers. And now the same trend as we see with all these other goods and services happens to computing. So computing is being democratized. And being democratized means that computing is available as an infinite resource. You just tap into this resource, and if you need more compute power, you get more compute power, just like the supermarket where you can get food. However, as things change, as we move from one phase to the other, you have to be careful that you don't hold on to old traditions. And one way that we, as humans and as scientists, survive in a complicated world is by using abstraction. And what does abstraction mean? Abstraction means leaving out irrelevant details. Now, the thing is that certain details are relevant in the past that might not be relevant anymore in the future, and vice versa. Certain details suddenly become important that you didn't care about in the past. For example, here, if you were a tailor, you would have to deal with very different things than when you work at a big box chain. If you're a tailor, you have to make measurements, you have to kind of know how to sew. When you work in a big box chain, that is really an impediment, because you only get frustrated because what you're doing is you're selling cheap clothing that people throw away after a year or something, and you just have to sell more and more, which is a completely different skill set. And I'm not saying that one is better than the other, but it should be obvious that the old-fashioned tailor wouldn't do a good job when they would have to sell jeans. Now, how does this apply to programming? I'm showing you here a little program. Don't worry. You don't have to understand what this program does. The only thing that I want to ask you is to look at each of the statements in this program. Okay? So you look at the statements in this program, and they all look the same. So the first statement there, int x equals 7, looks exactly the same as the statement at the bottom, HTTP response equals URL.get HTTP request. But that's just, the first one, the cost of these statements is extremely different. So the first statement is instantaneous. It takes a split second to compute. Whereas the last statement takes, in human terms, decades to compute. So let's make that a little bit more clear. If you look at the time that it takes to do certain computations, if you have a communication inside the computer, in human terms, that would take 1 second. If you have to read something from memory, that will take a few minutes. But if you send a packet across the internet, in terms of human time, that would take decades. And the problem is that our programming technology is still based on 1950s technologies. Our programming languages haven't really changed since the 1950s when we were doing Fortran and so on. So a program, when you write a program, you compose it using statements. That's the semicolon that you see there. And the individual statements change the state of the computer. And so I think we are in big trouble here because the world is changing, but our programming languages don't keep up with it. And to get a different feeling of this time scale, if you're sending a packet across the internet, in human terms, that would mean that you send somebody by foot to walk across the US, take a sailboat to Europe, deliver the package, take the sailboat back, and walk back. Okay? And we cannot speed that up because we're limited by the speed of light. And if I've done the math right, I was a bit jet-lagged, so it might be I might be wrong. But if you look at 1 week of CPU time, if you translate that to human time, that would mean about 40 million years. So in some sense, computers are very remarkable devices, because I cannot think of any other branch of engineering where we built a device that can run for such a long time. So don't complain if your computer goes down, because it has been running for millions of years, so give it a break. Whenever you're faced with a dilemma like this, I use a special trick. And this trick is not unique to me. It's very well known, actually. But a nice way to learn about this trick is via this book called Botany of Desire by Michael Pollan. So what he does, he asks the question, are the potatoes there for us? Or maybe are we there for the potatoes? Because we eat potatoes, but without us, potatoes cannot grow. So we take really good care of potatoes. We even have a university that's all, in the Netherlands, that's all, dealing with potatoes. And I would like to remark, potatoes are non-native plants. So maybe we should get rid of potatoes from the Netherlands. I don't know. I don't think so. Then there's another guy, Kevin Kelly, who argues that humans are the sex organs of gadgets. What does that mean? Well, it means that the gadgets need us to reproduce. So what these gadgets do is they make us addicted to them, such that we are building factories that produce gadgets. Now, this is not as crazy as you think it is, because computers are already, designing new computers. You could not design a computer without the help of a computer. So the human role in this chain is very tiny. And really, these gadgets, if you think about it, we are the slaves of our gadgets. And one way to look at cloud computing is that this is computers exploiting us, and we put them in a nice cozy data center that's nice and warm, and we have people that kind of take good care of them, so they are happy. Now, maybe this sounded all crazy, but the mathematicians have used this principle of inversion of control for a long time. And mathematicians call this duality. And duality means reversing the arrows. And here's what you see. If I said, A is there for B, if I turn the arrow around, then I ask the question, is B there for A? And this is a very, very powerful technique that can solve a lot of problems. It allows you to see correspondences between things that at first sight you don't think are related. So let's look at an example of this duality. If you look at electrical engineering, there's a duality between capacitors and resistors. And why do I like that example so much? Well, when I was still in high school, I could never remember those formulas, especially the one for a parallel composition of resistors. That's kind of the weird thing with the 1 over R. But the great thing of this duality is that you only have to remember one set of formulas, and you get the other set of formulas for free, because resistors and capacitors are dual. And so if you look at many other branches of science and mathematics, duality appears over and over again. And to take this back to our program, the program that I just showed you, in order to define the meaning of a program, we often use something called denotational semantics. And there you can define the meaning of this composition in two ways. One way is to use direct semantics. And again, you don't have to understand this looks like, scary math. But if you look at the line on the bottom there, it says in order to execute the second statement, you first have to execute the first statement. Well, if that first statement takes 10 years to finish, S2 will be waiting for a long time before S1 terminates. What would you do in practice? Well, if I would ask somebody here in the audience a question and it would take 10 years for them to answer, I would not wait 10 years. Definitely not. What I would do is I would hand you my phone number and say, call me back when you're done, and I would go on with my life. Well, that's exactly what you do when you do continuation semantics. In this case, S1 takes a continuation, this is the phone number for S2, and what this means is that when S1 has terminated, it will call S2 and says, here, I'm done, you continue. So what you see here is that we have inverted the control. We have dualized the computation. Instead of S2 waiting for S1, S1 will call back S2 as it sees fit. Now, back to cloud computing. What I've identified that we need to really tackle this problem of cloud computing is that we have to focus on 3 details. So these are 3 details that in the old style of computing we can abstract away from, but that become really relevant when we move to the cloud. And these happen to have, all start with a V, so that's quite nice. So that's volume, velocity, and variety. So I've already said a little bit about velocity. That has to do with, whether I wait for something or whether I get called back, whether I push values to my computation or whether I pull them through. The other dimension is volume, whether, you have a lot of data or a little bit of data. And then the variety has to do with what kinds of data you have. Obviously, I don't have a lot of time to really explain this, but that's why you have to come to my lectures and read my research papers where I explain all about this. So, to conclude, everything will be democratized. That is inevitable. You cannot stop progress. We have seen many, many examples, and the same now is happening with computing. Cloud computing is just computing becoming a commodity. Computing becomes like water or electricity. You can get computing on demand at elastic scale. However, when we make this transition, the world is changing, so we have to adapt to this world. And I would argue that a lot of the research and a lot of tools that we developed as computer scientists have not fundamentally changed since the 1950s. They have not changed since the invention of the computer. But the computer has changed, so we have to change with it. But to end with a famous quote of a Dutch soccer player, every disadvantage has an advantage. The fact that computer science is behind practice gives us also opportunities. It provides a full employment theorem for scientists, and it will keep us off the street for the next 10 years. So, thank you very much.